So what is non-commutative space? So it's two things which interact in the same Hilbert space. On the one hand, you have the algebra of functions, which can be non-commutative. Okay, so you have the Hilbert space, which is a common stage, and then you have the algebra of functions, and on the other hand, you have the line element ds. Okay. Now, what I want to explain briefly, and is why is there an advantage of taking this algebra of functions to be non-commutative? Well, we have already seen that for the quantum sphere. The beauty of the quantum sphere is that it's homogeneous, but for a quantum group. So it's and you need non-commutativity in that respect. Okay, but why is it useful in the case of ordinary physics? Why is it useful? The answer is so simple. The answer is that when you look at this enormous Lagrangian that we had, which was the Einstein action SE plus the standard model action, okay. Well, the first thing that you should do is look at the group of symmetries of this action. Now, the group of symmetries of this part is the group of diffeomorphisms of the manifold X, okay? And the group of symmetries of the standard model is not that, but it's the group, if you want, of maps from X with certain regularity, from X to the small gauge group, whatever it is. Okay, let's say for simplicities that we take SUN. Okay. Okay. So the full invariance group is not the product of these two groups. That would be too simple. It is a semi-direct product of these two groups. And why semi-direct? Because when you take a diffeomorphism, it will shuffle the points. Okay, so it will not act by the identity on the points. So it's a semi-direct product. Now, the obvious question is, you know, in French, one says that I think at the time of Einstein, so the part of the standard model was called la cabane en bois. So if you want, this is supposed to be very beautiful, and this is supposed to be ad hoc. So in fact, we would love this sum to be a single thing. Okay, so and we would love this sum to be a single thing which is purely geometric. But if we want to do that, we have to find that this semi-direct product group, in fact, it should be the group of diffeomorphisms of a single space Y. And as you know very well, I mean, this was the motivation behind the Kaluza-Klein ideas. Okay, but mathematicians prove theorems, and among these theorems, there is a fact that if you take any manifold, any dimension you want, the connected component of identity in diff Y is a simple group. So it cannot have this structure. It cannot be a semi-direct product of this type. Forget it. Okay. And now comes exactly the beauty of the non-commutativity. Okay, in a very, very simple manner. So what is the beauty of? I want to raise the other board, but. Okay, so here comes the beauty. So the beauty is the following. The beauty is that, you know, if you think a little bit, you'll find out that diffeomorphisms of a smooth manifold X is simply the group of automorphisms of the algebra of smooth functions on X. Okay, I mean, this is, you just look at characters, and that's it. Okay. Now, so what we want to have an algebra which is not just this. So let's take an algebra A, which is okay, and let's look at aut A, the group of automorphisms of A. Now, if the algebra is commutative, like it is here, there is no natural subgroup. If there was a natural subgroup, it would be normal. But if the algebra is not commutative, then we have inner automorphisms. Okay, and in all what I am talking about, we are working with complex numbers, so all the algebras that we take are star algebras. So the inner automorphisms are of the form f goes to u f u star, where u is unitary. So u satisfies u star equals u star, u equals 1. Okay? Now, because these inner automorphisms are natural, they form a normal subgroup in the group of automorphisms, star automorphisms, if you want. So you have this exact sequence. You have this exact sequence which tells you that you have a normal subgroup. It's very strange. You always have a normal subgroup, which is in automorphisms, when the algebra is not commutative. And now, if you take the simplest possible guess, namely you replace this algebra of smooth functions by matrices of smooth functions. I mean, there is no simpler guess. Okay, so for instance, I take 2 by 2 matrices of smooth functions. Okay, what does it mean? It means that I write 2 by 2 matrices f11, f12, f21, and f22, and I multiply them as matrices. Where when I add and multiply the elements, I multiply them as smooth functions. Okay. The new feature of this algebra is that it's non-commutative, only slightly, of course. Okay. But then you can compute this exact sequence in that particular case, and what do you find? You find exactly the same exact sequence that was revealing that was revealing. No, I want to have this one going up. Here, I want to leave it to make it leave.
No, it should.
Okay, now, oh no, up. Yeah, put it again. Very good. Okay, with some trial and error. Trial and error is of course the key to science. Okay, so we get the same group as this guy.